All right, students, back in the physics classroom. It's Mr. Gustin here. Still stuck? Having a tough time figuring this thing out? Okay, I will give you a few hints, but I am not going to walk you through the whole thing. You'll at least have to plug your own numbers in and calculate your own range. Let's think about the ramp first. The first step that I'm going to have to do is figure out the velocity at the bottom of the ramp. That's kind of the most important part here to determining the range. I need to know how quickly this thing is moving as it leaves the ramp in order to figure out how far it's going to travel. All right, so let's take that first step. Well, down the ramp is going to be F net parallel. That's where this object is going. It's moving down the ramp. Let's think about the forces that are acting down the ramp. Well, we know it's going to be mass times acceleration for down the ramp because there's a net force that shouldn't be zero. We know the forces acting parallel to the ramp are going to be Fg parallel minus the force of friction. Okay? We know these things. Let's keep working this through. The mass times the acceleration is going to be equal to Fg parallel, which we should know is Fg sine theta. And the force of friction we know is coefficient of kinetic friction times the normal force. Still, I'm not sure about all these things yet, so let's keep plugging some stuff in. Mass times acceleration equals, I'm going to convert Fg into mg just to make sure I have some more variables. Sine theta equals minus the coefficient of kinetic friction times the normal force. Well, the normal force we know is also equal to this component here, this Fg perpendicular component. There's my parallel. But the Fg perpendicular component, I can probably go ahead and plug Fg perpendicular in for Fn as well. And Fn, when I substitute in Fg perpendicular, ends up being mg cosine theta. I've got this expression. The reason this expression is so useful is because I have boiled it down to its most basic variables. Like, I can't plug anything else in that makes this more basic, right? Mass, nothing plugs in for mass. Acceleration, nothing plugs in for that. Mass, baby g is a constant. I know my coefficient of kinetic friction. I solved for it in the intro video, mg cosine. Again, folks, I don't have a balance at home. I don't have a scale at home. I cannot figure out the mass of my object. That's okay. Check this out. Mass shows up in every single term, which means I can divide both sides by mass. Mass has no impact on how quickly this thing accelerates. I end up with my acceleration being equal to baby g times the sine of theta minus the coefficient of kinetic friction, which I solved for in the intro video, times g times cosine of theta. I'm not solving that for you. No, you figure out what your acceleration is. You figure out how quickly this thing's speed is changing from initial to the edge of the ramp. Once you do that, we have step like 2b, or 1b. So this is 1, this is like 1b. Once I know my acceleration, now I got to figure out what is the speed going to be at the edge of the ramp. Well, what are some things I know after finding acceleration? Well, I'll know my initial velocity is 0. I'll know that it's going to travel a distance of 1 meter. I'll know the acceleration is equal to whatever I found it up there. Initial velocity, position, acceleration. I'm looking for final velocity. That's my unknown. I know an equation that I can use that includes velocity, position, and doesn't include time. It's my squares equation. I'm not going to solve that for you. You solve it. Which one is V ramp? Right here. That's your V ramp. Got it. Got it. If that's all the help you want, If you think you can solve this projectile problem on your own, hit pause, solve the velocity for the ramp at the bottom, and don't watch anything else. If you've already watched all of this and you've done all of this and you're back and you're scratching your head, you're like, I can't figure out how to solve this not horizontal launch type problem. Okay, fine. Let's solve that. Here's how we can go ahead and solve for the range. Let's think about what's happening right here, right as it leaves the ramp. Let's draw a picture of that. Right as this object leaves the ramp, we know it's launched at an angle of 30 degrees downward. It's launched like that. We know it's launched at a height of 1 meter because I measured that. You measure your height. My height is 1 meter. And I'm trying to find this change in x right here. Remember, when it comes to launch problems, the one thing we have to remember is that time in the y direction is always equal to time in the x direction. I need to figure out how long this thing is in the air first before I can figure out how far it's going to go. Let's start with the y direction. In the y direction, what we see, what do we know, rather? We know, we don't know. Let's pick an equation. Well, first things first, let's find our initial y velocity. Okay, so at the bottom of this ramp, we know that there is an initial, like Vy, and there's a Vx because it's launched at 30 degrees. Let's find those. Vy is going to be equal to sine of theta times V ramp. Vx is going to be equal to cosine of theta times V ramp. Unit 1 stuff, kinematics type stuff. We're still breaking our vectors up into components. Okay, once I do that, I know my initial y velocity. Got that. I know my change in y. What am I looking for? I'm looking for time. Do I know my acceleration in the y direction? I always do. It's always baby g. What am I looking for? Time. I know my equation. Change in y equals initial velocity times time plus 1/2 g t squared. Okay? It looks like I'm going to have to use a quadratic equation to solve that. I may have to use a quadratic solver. That's okay. I'm not asking you to know how to use the quadratic formula. If you have a quadratic solver, go ahead and solve it and pick a reasonable answer. Time probably shouldn't be negative, right? Time shouldn't be less than 1. Time probably shouldn't be more than 1 second either. It's only falling a meter. Use the quadratic. Pick a reasonable answer, all right? Once we find time, well, it gets pretty easy now. In the x direction, we remember there's only one equation. Change in x is equal to the velocity in the x direction times time. That's our constant velocity equation. There's no net force in the x direction when an object is in free fall, so that's the only equation we could possibly use. We're going to go ahead and solve by plugging this time in for this, finding our change in x. That's the spot where you'll put your target. No, I'm not going to solve it for you. I've done the hard stuff. Hopefully it makes sense. Hopefully you can take your data, stuff you measured, you plug it in, you set it up, you take the video, you place the target, you turn it in on Canvas, and we'll see how you do. See ya!